Okay, so welcome to this part three of this revisions series of chapter three, namely single stage amplifiers. And in the previous video, I did one mistake when I was describing the voltage swing limits of the diode connected device. So I'll just quickly address that. So let us just say that we have a diode connected PMOS load and I have some circuit over here and I am sensing my output over here. Okay. So the fundamental limit to the output swing here will be imposed by what? Is that since this guy is always in saturation, so it can either be always on or off. And we can understand that this guy will become off if V out or the gate voltage value increases quite a lot, right? So that limit is set by this equation that we already know for PMOS, which is given by this guy, right? That this overdrive must be greater than 0. And so we can just set the upper limit for our V out. So this is basically the swing limit that we have for PMOS load on output. And this is the upper limit of output. And the lower limit will be set by the circuit which is here. And if it is common source amplifier, then we have already established it before that that will be V in, right? And that will be Vn minus Vth, and that will be the lower limit of the output swing. And if I have a basic current source as PMOS load, then V out, the upper limit of V out will then be affected by the drop, the minimum drop here, and the minimum drop here in that case will be what? It will be what? So there are two ways to describe that. Either you can say that some bias current is flowing here, and then you describe this VGS, and then you subtract it. All that you can do. But what should be the value of V out to maintain this guy in saturation? Yeah, so the value of this V out must be less than what? It should be less than VB minus VTHP. So as it is just well simple coming from this kind of logic only, but the difference is that now the gate voltage is VB. And so which of these two cases pay better depends. For example, if my V bias is equal to VDD, so these two cases are basically identical. But here basically it is tied here, and here I can basically change my VB and make things make maybe try to increase my V out a bit more. So that is the kind of freedom I have here, which is not present in diode connected load. So this was like a very quick overview, and you can just work out the calculation of this to just be sure that I have calculated the correct thing. Okay, let us do it just for the sake that we are again not doing some kind of a silly mistake. So yeah, this is VDD minus VB, right? So this VDD minus VB minus VTHP. So basically this guy must be less than VDD minus V out, right? And so you can just say that V out is fundamentally limited by VB plus VTHP. So yeah, this plus sign mistake I was doing. So yeah, so this is the upper limit of V out in this case. And so you can basically understand that here, if VB is VDD for time being, so V out can actually swing a bit more, right? In this case, as compared to diode connected load, and thus diode connected load does suffer from swing limits, because here it is reducing by this term and here it is increasing by this term, up to what extent the output can fundamentally swing. Great, cool. So that being out of the way, that now we are actually able to appreciate that for same for VB equal to VDD, the diode connected device has some voltage headroom issue, and this guy does not have. Let us now finally go to the source degeneration, common source degeneration amplifier. And let us just give this a real quick discussion, and then we can just move to other remaining amplifier topologies. So the idea here is that for simplicity, I'm drawing a drain resistive load. Here you have your V out and here you have your V in. And now the idea here is that we are placing a degeneration resistor RS over here. And why is that so? Like, why are we doing that? This idea is the idea of feedback. And if you have studied control system, we basically fundamentally use feedback to reduce errors, yeah, and to improve linearity, to decrease sensitivity to noise, all that. So when we solve this equation, how it works out as that if you just try to follow the if you just assume for time being that the body effect is zero, and you are considering the channel length modulation is zero and body effect is non-zero, so you can just derive the equation of gain as minus gm rd gm plus gmb times rs plus 1. So you can see here that the degeneration basically decreases the gain, and I think it's a fundamental fact that we all know that bandwidth times gain is kind of a constant. So this degeneration basically is help the kind of action is helpful when you are looking forward to increasing the bandwidth, but yes, we are sacrificing on the gain. Also, we can see that body effect basically also is decreasing the gain of this particular configuration. But why we are really needing this degeneration is the question over here, right? So, for example, if I were to talk about how much, if let us assume that I'm applying some V bias over here, okay? And let us say that we already know that this V in includes V in bias and the small signal V in. So let us try to understand that how really currents would be flowing. So we know that certain current is flowing from here to here, and a certain current is flowing from here to here, right? And so here there will be certain voltage developed, let us call it Vs. And here also there will be certain voltage developed, which is V out only, but let's call it Vd. So what this degeneration is really doing? What this degeneration is really doing is that when you try to write VGS, what is VGS equal to? VGS will be V in minus I, the current is flowing, minus RS. So this is the negative feedback action. We are seeing that the input gate to source voltage is effectively decreasing by this degeneration term. And what will be the need of degeneration? I have already hinted I have already hinted on this when I talked about control system, negative feedback, and all that, but you should be able to explain that what is the actual need of degeneration that we are just inserting another resistance. And now again, there can be a good doubt here that we initially said that we don't want resistive action. So yeah, you can again replace this resistor by some other device which can act as a load. So that can be again all those different kind of loads we discussed, and as per the swing limit constraints, you can accordingly decide that what kind of load you want here. And here also we have already discussed that you can have a variety of loads, which we have already discussed. Okay, moving ahead, let us talk about now some other amplifier topologies. And let me just go before common gate, let me move on to the source follower, which is also a kind of a voltage buffer. So here you can insert a variety of loads again, that you can have a resistive load or all the kinds of load which I have already discussed. Let us take a very simple case to understand it intuitively. Let us say that I am applying some V in here and I'm biasing this guy by I bias. So I'm basically fixing the current through this transistor and I'm sensing my output over here. So now I know that in small signal, what will happen in my small signal, this node will get open, right? This node will fundamentally get open, and here is my V out. So you can understand for any kind of swing happening here, the current can't flow because it's open, which means that V out must follow V in. So I can directly say that V out equals to V in. That means the small signal gain is approximately equal to 1. Very intuitive, but also very crude way to estimate what the gain is. But the actual gain expression in general format, if my circuit was kind of like this, when I'm considering body effect and channel length modulation both, is of this form. And again, you can just quickly derive it with just by using the lemma that you're just saying that here this R node guy is present. So in small signal, this guy becomes short, right? So this since this guy is grounded, it comes in parallel with RS, as you can see here that RS is in parallel R out, RS in parallel R out. And then again, you can say that since your uh, your current when you have to find, now you have to draw the small signal model. You can solve here also, and just by KVLs, you can achieve or arrive at this result. Should you remember this formula? I'll say that yeah, it's worth it to remember this formula. It's because you can actually appreciate that the buffer action is not ideal, right? Because this value will be approximately equal to 1 only when GMB is first of all zero or negligible. Also, when this term is much greater, that is a different story. But we can intuitively understand that this guy is a bit less than one. So the ideal buffer action is not really achieved, right? It's not really achieved because this term is kind of less than one. But yeah, we call it or we try to use the word buffer, but it's not a very common used circuit because of again, it does introduce some non-linearity, noise, distortion, all that. But this is a talk of later. But we should just have this in mind that if you have input here and you have output here, it's kind of trying to act like a voltage buffer. Let us move to the next circuit configuration, which is a common gate amplifier. Again, here you have a plethora of choices of loads, but for trying to keep things simple, I'll just go with a just loads here and here. But now we understand that to achieve loading, we can have various transistors in various configurations, like we already discussed, diode connected, triode connected, current sources. So it's all up to us. But for just for sake of simplicity, here I'm just keeping it RD, and here I'm keeping it as RS. But now we can understand that I can replace easily the RS expression with whatever is the effective transistor R out seen from here, and whatever the transistor or circuit R out is seen from here. So I think now these things are quite obvious to us, so I'm not really commenting on that. So this RD and RS is in a way a general way of representing the loads, where I'm not really saying that this RD or RS is ohmic in nature. Okay, so these can be your transistor based nonlinear loads also. Okay, so I think if this idea is clear, if I'm applying some V in here, what's my V out here? So again, you can assume that lambda is not equal to zero and gamma is not equal to zero, and you arrive at this very hefty equation. Have I memorized it? No, because I have not really in my experience so far, although my experience is not that big, but I have not really found any much of a need of this expression. So how do I personally go about analyzing this amplifier intuitively? Is that I just assume that my lambda is zero, and if my lambda is zero, does that ease out things for me? It kind of does. So I assume that my lambda is zero, and I can just say that my gamma is non-zero. So what we find here essentially is that if you are analyzing it in small signal, how will this guy look like? That this guy is grounded, and you here have this resistor RD, here you have this resistor RS, and what will be the current flowing through here if this is V in and if this is V out? The current that will flow through here is only the current. See, the thing is that if there was a R out here, current would have been flowing, some current would flow through here, some current would flow through here, which would have complicated our life. But now, R out being out of the way, only path current has is this guy. And so we already know now that the small signal current will begin by GM plus GMB times minus or times VGS, which is basically minus Vn, right? So this is the small signal current flowing from here to here, which means that if this guy is grounded, right? So what will be the voltage at V out if this current is flowing? RD times GM plus GMB, right? Great. Times V in. So the gain, what is the intuitive expression for the gain here? Huh? What is the intuitive expression for the gain here? And again, it is zero again, since current is flowing from lower to higher potential small signal, so this would be a plus sign. I think you can understand it by simple KCL KVL. So the gain is GM plus GMB times RD. This is the intuitive result for the gain. And if you consider R naught, so this is how the general equation will come like, but I personally don't find it to be that worth it. You can easily verify that our intuitive expression, and these are in order if you just approximate R naught as infinity. So you can just divide R naught here. So R naught can just come here. So this term will go to zero. R naught will divide here and here. So these two terms will go to zero. And then you can just arrive at the expression comfortably at what we have already arrived, right? So that being said, these are the three amplifier configurations. Okay, great, cool. And finally, let us talk about the cascode stage. Okay, let us talk about the cascode stage. And here also the general expression for GM is this kind of hefty and things you can I always derive it by using the small signal model, applying KCL, KVL, but here the agenda is to like arrive at the result intuitively. So let's try to arrive the result intuitively. And the thing that we must realize is that in these kind of problems, what guy is giving us the most problem is lambda. So I'm just saying that lambda is equal to 0. And also just for the sake of simplicity, I'm saying that gamma is also equal to 0. Okay, so now what can I comment upon GM? When I'm trying to find GM, I think we already know that we short the output and we see that what is the current flowing through this guy. And since it's a small signal analysis, this guy will also be shorted. Great. So now the current which is flowing here, which is I out, because I out has only one path, right? Because I'm seeing through this way, and I'm saying that let us say that here I have biased this cascode by current source, so this is basically open, right? So some current is flowing here, which is I out only because this guy will be open in small signal. So what is my GM? It is simply I out by Vn, which just happens to be GM1. It is approximate, by the way, okay? And my R out is what? If I see this transistor as reference, if I'm calling this guy as M2, this guy as M1, so if I'm seeing this transistor from here, so I can for this transistor, this guy is RS, right? This guy is RS, and this guy will is shorted, correct? So the resistance it is seeing at its RS for M2 is R naught, right? And so now, if you recall what is the resistance seen at a drain, it is RS, which is here, is R naught plus, plus what? R naught plus what is the expression? And this is R naught 1 plus R naught 2 plus R naught 1, right? R naught 1, R naught 2 times GM. So this is approximately equals to R naught square GM if R naught 1 and R naught 2 are equal, right? Because we know that R naught is a large value, which means R naught square is much, much greater than R naught and R naught 2. So this is the approximate value. So what we basically arrive at, the result we arrive at is that the gain of this cascade stage is equals to what? It is equals to minus GM square. If GM and GM are also same, it is a very brute approximate result, but it is just giving an intuition to us that the gain of this cascode stage is so high, right? And what is the condition of this cascode? This guy is working as a common source, right? So input device is common source, and for this guy, the input is at what? The input is at the source and output is at stage. So the output stage is the common gate, right? So this is the basic idea about the cascode. And yes, you always have this general equation that you can always are free to derive. But this kind of method gives us a better approximation and intuition. Great. Let us again try to analyze. Now, again, here I said that lambda is 0, but again, you might now wonder that what nonsense am I doing? Like, right? Like you are saying that for GM, I just said that my lambda is 0, and then I derived all that, and then for R out, I'm considering R out. So the idea here is that we are just trying to use some intuition because R naught is a very huge value. So some current division and all will take place, but that current division won't be that huge, right? Because R naught is a huge resistor, so not a very significant amount of current will flow through it. So that's the basic idea that for derivation of GM, I assumed my lambda is 0, but for a derivation of R out, I'm not considering my lambda is 0. That's the basic idea. Because if I'm considering this lambda as 0 here, my R naught then will become infinite, and then the things won't make sense anymore. But for derivation of GM, the assumption that lambda here I'm approximating it as 0 is quite alright. Okay, so that being said, this was a discussion about Cascode. Now, Cascode has two properties that we should also keep and bear in mind. Is that Cascode has a shielding property. Okay, Cascode has a shielding property and can also be used to reduce mismatch in differential signals. So this is a very important property of Cascode, and I think maybe I'll discuss it in another video in an example. As of why Cascode device is good, why Cascode device is great for shielding voltage at certain nodes, and which is finds its application in current mirrors, and also that Cascode also reduces mismatch especially like when we are applying it in differential applications, and that's something which we'll discuss later. And this basic cascode, where both the CS and CG stage are of the same type, it is also called telescopic cascode. There is another cascode is called the folded cascode, where you are saying that one of the stage is of NMOS or PMOS in nature, and the common gate stage, okay, and the common gate stage is PMOS in nature, so it is folded, right? So that's why we call it the folded cascode, okay. And you won't be able to appreciate it much at the moment. When we'll go and maybe in future discuss about op amps, then this whole structure will seem to be more meaningful to you. But this jargon, let's keep in mind that this kind of a cascode, where one of the devices NMOS, another device is PMOS, and you can interchange them also, this is your folded cascode, okay. And you need an additional current source to bias it. For example, we know that here we need some current source or some load to bias it. So the same thing you need here also to bias this guy, right? So that's the basic idea, that an additional current source is needed here to bias the folded cascode. Now, there is one more thing that I would want to discuss about cascode is the large signal behavioral cascode. So there are three things that I basically want to discuss exclusively later on, using an example also in the book by Razavi. That is one, large signal analysis of cascode. That is something that I want to discuss about. Second thing that I really want to revise is the shielding property of the cascode, and also that how it is able to like mitigate the problem of mismatch in a differential configuration. And that is pretty much it. That's pretty much the theoretical summary of the chapter 3. And these three guys I will discuss in next video, which will be the final video for this chapter. And yeah, and there's one thing that maybe I can discuss, a final thing that I can discuss is about the large signal behavior of CS amplifier. So I think this is also quite all right. The graph I've already drawn, that initially when my V in is zero, so no current is flowing, which means that no voltage drop is there. So with this here, it is VDD. No voltage drop means V out is also VDD. Great. And initially V in is too small. That means that my transistor is still off. That means voltage drop is zero. So it is fixed at VDD. Now, when my V in just becomes greater than VT, right? When my V in just becomes greater than threshold voltage, MOSFET turns on. And that means that since V in value is small, which means V in minus VTH or overdrive is small, transistor is in saturation regime, right? And so certain amount of current will flow, and so as eventually the current increases, the drop increases, which means that V out value decreases, because VDD minus effective resistance times current, right? So the V out value decreases, and now as when V in is high enough, the device goes to triode regions, which means that the current now stops to depend by square of input, and so the current dependence is now linearized, and so we see here also that now the V out value is not decreasing that sharply. So this is the last signal characteristics of CS amplifier. Can we also draw the same for common gate? So let us just discuss it now that we are already doing this. So for common gate, what will be the large signal characteristics? V out, V in. Okay. So what will be the raw signal characteristics over here? Again, V in, when V in is zero. So here we must understand that this V in uh, is the small signal that I'm applying over here, right? And technically, I'm not applying any bias here as such. So when we are analyzing here, we were saying just about like when we are talking about input at the gate, here there was bias also, and there was small signal also. But here, the bias is applied here, okay? So now we must be able to appreciate that when V in is zero, this guy is already on, okay? So V out will be at some value, let us say some current is flowing, and if small signal V in is zero, it does not matter because some bias current might still be flowing, right? So that's the basic idea. And as you will increase the VN more and more and more and more, so eventually the device will get off, right? Because when when VN is basically equals to VTH, right? When Vn is equals to, or basically the idea what I'm trying to convey is then when large signal, and I'm applying some large signal at Vn, and I'm saying that VB minus Vin is equals to VTH, or alternatively, Vn is equals to VB minus VTH, this device will turn off, right? And when this device will turn off, that Vout will at that time go to VDD as we discussed earlier, which means that the graph can be approximated by something like this. And I'm not really going into the main detail of how the shape will be like, but the graph should kind of go from here to here, right? I'm not really interested in the shape at the moment, but we are just trying to get an idea as of how things should play out if I'm just increasing the signal here again and again, if I'm just increasing the signal here from small to large. Great. And now let us also just, now that we are already discussing this, so let us, for sake of completeness, just also discuss about the source follower. Okay. And here I have my output, here I have my Vin. So here I have my output, here I have my Vin. So again, here we can understand that when Vin is 0, so now again, no current, which means voltage drop is 0. So Vout is again here at 0. And if it is a ideal buffer, it will just go like this. But we know that we can intuitively kind of also say that Vin must be at least equal to VTH, right? And then only the MOSFET will turn on. So even if you are just assuming very idealistic situation, still this graph, this is not the graph that we'll see, but the graph will be kind of like this, right? Because after VTH only the conduction will start and then output will start following the input. And the slope again will be, slope will not, will be a bit less than 1 because it's not an ideal buffer. So that is the last single characteristic that I wanted to talk about. And I think that's yeah, that's pretty much it. And when Vin is too large, okay, when Vin is too large and device basically goes into triode regime. Okay, so this is again, this is, we are talking about saturation. But what if this Vin is that much high that the device goes into triode regime? Then how should this graph look like? Vin that much high, the device is transitioning into triode regime. So that is something that will be clear to us by large signal analysis, that which we are already doing, but we should also write equations for it. So I think this aspect also I'll discuss it in the next video, because this, I think this video has gone a bit too long. So let us just summarize the things that we want to deal with in the next video. That is, first we'll discuss about what is left in sequence. So we'll just talk about the large signal behavior of source follower, as we are typically interested what, how will it behave in triode region, that is the large signal analysis. And then we'll look at the behavior of cascode in large signal. So these two things are namely left, and I think apart from that, we have basically covered the chapter 3 theory in entirety, and we'll just cover one example for cascode in the next video, and that will be the final video for this chapter 3. So again, thanks for watching, and I'll see you in the next video. Thank you.